Transposing a matrix is very easy, and it's the same as with vectors. You may need to do this when you want to multiply two matrices, but they're of identical sizes, and they are not a square matrix. Then you would need to transpose the second matrix so that the number of columns from the first matrix is equal to the number of rows in the second matrix. And this is done by using a single quotation mark. So let's say that we want to multiply the first and the second matrix. You can see that the first and the second matrix are both of 3 rows and 4 columns. If we directly try to multiply them, this will not work. So first matrix times second matrix, this will not work. It says inner matrix dimensions must agree. This means that if you place the dimensions of the two matrices next to each other, so if you say both of these matrices are 3 by 4, so 3 by 4 and next to it 3 by 4, you have 3, 4, 3, 4. The inner 4 and 3, the second and the third values are not the same. If you transpose the second matrix, it will now be a 4 by 3 matrix, so you will have 3, 4, 4, 3. The inner dimensions will be the same. The columns and the rows will be equal. So if we do this, if I simply transpose it with a single quotation mark, it's now working, and our final result is of the size of the outer dimensions of the tree. So we have 3 rows and 3 columns, and it produced a square matrix. Now let's say here multiplication with transposing, like this. Alright, now let's say that you want to take the diagonal, you want to extract the diagonal of a matrix. We are first going to start with a square matrix. Our square matrix has a diagonal of 1, 4 and 4. We want to extract this diagonal. The way to do this is to simply use a function called diag. I really don't know how to pronounce it, so diagonal of, short for diagonal, diag short for diagonal of square matrix equals diag of square matrix. Let's run it, and we get 1, 4 and 4. Now keep in mind that we get these values as a column vector. This is a column vector, one vector. You can see down here, diagonal of a square matrix has 1 semicolon 4 semicolon 4. Each of these values is its own row, meaning that we have a column, we have a vector column. Now let's take the diagonal of a non-square matrix. So diag of non-square matrix equals diag of non-square matrix. Let's run it. Let's press this one, and we get 1, 3 and 3. Now let's see what is our non-square matrix. You can see that we have 4 columns here and 3 rows. This is a non-square matrix, but as you can see, we still got 1, 3 and 3. We still got 3 values for our diagonal. So the way that this function works when it is applied to a non-square matrix, it simply starts from the first element on the first row and starts taking its diagonal and takes it to wherever it ends. In this case, it's 1, 3 and 3. You can shift the diagonal, meaning that let's say that we want to take the, let's start first with our square matrix. So square matrix. Let's say that we no longer want the 1, 4 and 4, but we want to take the 4 and 2. This is also a diagonal, but it's an upper diagonal from our main diagonal. So we want to shift one up. So this is shifted square matrix, diagonal, shifted up. So diagonal, square matrix. And this is here how you shift it with the second argument to a diag function. The second argument is simply a number, and you specify to where you want to shift it. Now let's suppress this and let's run it, and we get 4 and 2. So we shifted it up. If you want to shift it down, so square matrix, so if you want to take 3 or 4, you will use, now I'm just going to copy and paste it, so shift down, you will use a negative number. Let's unsuppress this. So we have our matrix, we have shifting up for the 4 and the 2 and shift down for the 3 and the 4. If you shift it one additional side, so -2 and 2, you will simply get the numbers in the corners because there are no other numbers. And if you shift it even more, what will happen? You get an empty matrix. You don't get an error, you get an empty matrix because now you're trying to get a diagonal that's somewhere out here in the space, but there is nothing there. The same applies to the non-square matrix. So let's see the same examples. I'm just going to copy and paste them to not waste any time. So we're working on the non-square matrix now, and this is non-SQRT, and let's start with the 1 and -1. So let's run it. All right, now remember, this was our main diagonal. 1, 3, and 3 was our main diagonal, so we're shifting from that main diagonal. Our shifted up diagonal is the 4, 4, and 4. So this diagonal right here. And when we shift down, we get the 5 and the 5. If we keep shifting up, we'll get 5, 5, 6, and empty matrix eventually. If we shift down, we will get 6 and then an empty matrix. So we have less shifting in one of the directions because this is a non-square matrix. If this was a matrix that had more rows than columns, so if we had 4 rows and 3 columns, we would be able to shift more on the downside than on the upside. And finally, I want to show you how you can create a diagonal matrix from a vector. Now let's say that we have some vector, this vector right here, and we want to create a diagonal matrix out of that vector. The way to do this is to simply the diagonal matrix is to simply use the diagonal function and pass the vector to that function as an argument. So let's place this here and let's run it. And there we have it. We have the vector, and that vector is now in the diagonal of that matrix. Everything else is in zeros.